Welcome back from the break. Now we are ready to jump into the deterministic dynamic programming. That will be the tool for hand-in assignment number 2. This is also what I come to call the crown jewel of the course. Deterministic dynamic programming solves the optimal control problem that we've set up previously. So we have our criterion function here that we are trying to minimize, and then we have the dynamics that we need to fulfill. We cannot break the rules of the physics, and we have a given starting point. Then we're specifying where we would like to be, either with such a function or with something that is strictly given. In optimal control, the state variable x and the control are functions on this time range. So they are infinite dimensional. They are curves on this interval. X is continuous as it's a result of an ordinary differential equation, and u that we're searching for does not need to be continuous. It can be jump continuous, for example, if we have a problem that has classical bang-bang control, where we are jumping from one side of the control to the other, for example, full acceleration and then full retardation, if we are going from one point to another as quick as possible with limited controls. How is this solved then? We search an approximation to this solution by discretizing our state variable and possibly our control variable. For example, we're looking at the state variable here. So this is, we take our state x and then we follow here with the time, and it discretizes. So we have discrete time samples and we have discrete levels of our state. And we want to start here in the blue, and we would like to be here in the green at the end. So you could see this as the state of charge in a hybrid electric vehicle. So the state of charge can be empty and up to full, and then we have selected a number of discretization points in between, and then we're looking at how this state evolves over time. And in a hybrid electric vehicle, we are free to use this during our driving. So this is an example of where we're using one of the free dimensions to find a better solution than just using the traditional vehicle. So with a hybrid electric vehicle, we have one more free dimension. We can utilize the energy storage to shuffle energy between some points to other points, and we can use that degree of freedom to gain fuel economy. The most straightforward thing is that we can take electrical energy while we do the regenerative braking, and we can use that energy we got there during the next acceleration. Or on the other way around, if we have an acceleration, we know that sometime in the future I might need to brake. So then I use a little bit of energy and come back and recover that energy in the next deceleration. When we have done this, the result is a combinatorial problem. So it's a network problem that we have to go through the behavior from this point and then find the optimal path through this network to this point. The dynamic programming is searching for the optimal controls. So when we're searching for the control, we have some control actions here. So from this point we have 4 control actions leading forward, and this to the points that we can reach. And then from this we also have 4 reaching forward. So we're propagating and we're searching for the control actions that will lead us optimally to the end. We are searching the optimal sequence of control actions that minimize this, where this is then the end cost that we have, and this is the cost of our control actions. This is just a discretization of this integral, where we have decided what TB should be. TB is no longer free. And when we have TB fixed, then the only thing that we can utilize is the state at the final time. And then for each time step we are consuming resources like fuel or electricity. And we also have a difference equation here that tells how does the state change from the previous state and with the control that we have selected. And we have a given initial state where we started, and our state space, in, for example, state of charge, should be within the given interval. And finally we have our control that need to be inside the admissible range. This is called deterministic dynamic programming. If we add disturbance here, the disturbance WK that is stochastic, that we don't know everything about the problem. It might add a little bit of noise here, a little bit of noise here, and that disturbance then makes it stochastic dynamic programming. And that can be utilized to solve, for example, for uncertain situation with when we don't really know the traffic situation. So we have maybe some guess about the traffic population, about the magnitude, so that we can model it. So we get a disturbance model, and then when we have the disturbance model and we have our dynamic system, then we can solve it with stochastic dynamic programming. Coming to the basic algorithm, what Bellman realized was that we can solve for something that's called the cost to go function. And he realized that instead of focusing on getting from the start to the end, we can, by starting in the end, build up in a systematic way a cost to go function. We start at the end and then we proceed forward and we determine the optimal cost to go. So for example, we start here in this given point. We know that this is where we need to be. And then since we know that this is where we need to be, these guys here might be set to infinite values, or these two in terms of state of charge might be okay, but we have then regenerated too much electricity. But this is where we should be. Then we can, from this point, propagate the solution backwards and find out, okay, what is the optimal cost to go to the end from all these points. And we see this one has only one way to go, and that is this one. So we know that the optimal cost to go from this point will be given by this arc cost. And for this is the same, and for this is the same, and for that is also the same. But in these cases, the cost might be zero for these points also, so it might be better to just go straight over here. But this is an infeasible point, so this will not be available. So now we know that this guy is the lowest, and these are not feasible here, because with these we cannot get all the way up to that desired point when we have this network problem. So that's the basic idea behind deterministic dynamic programming, and this is what we want to solve with this difference equation. And to solve it, we start at the end. We assign the final cost to be the same as we have here in the final cost. And then we jump to a state that is earlier, so we jump to the preceding state. And then for all points inside the state space grid, so we loop over all points that we have available, and we search for the one that will give us the best result when we go from the current point to the cost to go that we already have. So this is a cost to go function that we have stored because we know what the optimal cost to go was there. And if we have come to the initial point, so we have gone all the way to the beginning, then we return the solution. Otherwise we decrease it with 1 and we go to the preceding time step and we search for all the points here for the best cost to go, and we store them all over. So an illustration of this is coming here. So here we have assigned our g. So all these costs here are given by the function g, so we have stored them. Now we start to go through all the points. So we start with this point and we look at what is the cheapest way of getting to the end when we have these costs for the arcs. So for this first cost, the arc 0 and the cheapest cost of these, so following this arc the cost to go would become 3. Following this arc, it would be 4. While if we're following this arc, the cost to go becomes 2, because it's 2 plus 0. Then we go to this point, and now we have stored that point there. Now we're coming to this point, and we're doing the same thing. We're finding what is the optimal cost to go and what arc should we follow. So we store both the cost to go and we store the arc that we should follow, and then we jump to the next one and do the same, and then we store once again the optimal cost and the best arc. And we continue like this. We search the minimum, store the cost, and store the best arc. And here same thing. We calculate the cost, we store the cost, and we store the arc. And the same thing here. Now we have completed all of these, and we know that the optimal point to get from all of these will be to follow that pattern. And we go to this grid point. Now we have decreased k one more. So we are at n minus 2, and we repeat the same procedure for searching through this grid. Your task in the hand-in assignment, it will be to calculate these arc costs. So you will be handed a point that says that you are right now in this point, and you can go to all of these points. Please return the costs for doing that actions. What would it cost to go to the different states? So your task here then is to calculate these costs for this decide step. Then there will be a wrapper around it that you don't need to program, which you will be given. And that is the optimizer that finds the best arcs and stores the best cost to go. The only thing that you need to calculate here in the assignment are the costs for the different arcs. Then the optimizer framework that you will be handed will figure out the optimal solution. So what you will have to do later then is to unwind the solution and just follow it to see what's the optimal way forward. For every arc you know where you are, and you also know all places you can go to. When you're about to calculate the arc costs, you can do it in two ways. One is to calculate the exact control signal that you need for getting between the two states, and from that you can calculate the cost for each arc that's in there. And that can be seen as a quasi-static approach. You are asking the question that, okay, how can I reach this final point from where I am? There is another way to go about it, and that is that you make a grid over the control signals, the possible control signals, and then you figure out what arcs will that control signal cover, and then you interpolate the costs for each of these arcs. So here you have a forward calculation approach. There is no principal difference between these. They have some advantages and some disadvantages depending on how expensive it is to calculate the arc costs. From a conceptual point of view, and in this course, I am suggesting that you work with this procedure. This is a little bit more involved to program, but can save some time in some applications. When you work with MATLAB, then it's important to utilize matrix calculations. So you calculate the whole bundle of arcs in one step. The arcs that you're seeing can be seen as a vector. So you have a vector valued function that you are calculating, or you will see later a matrix. So you do the computations for all elements in the matrix within one function iteration. And you also add boundary and constraint checks to make sure that you are fulfilling the constraints of the batteries, fulfilling the constraints of the electric machines, and fulfilling the constraints of the combustion engine. Pros and cons with dynamic programming. The pros are, you know that you will get a global optimal solution for all initial conditions. So provided the problem you have set up with the discretizations with the states, you will get the global optimum for all initial conditions. And you can have arbitrary complex nonlinearities inside the functions that you are iterating over. The time complexity complexity grows linearly with horizon. So if you can solve a small problem in a given time, then you know that you can solve a double length problem in twice the time. So it doesn't expand or explode in terms of time. And you can also use this output and solution as a reference for comparison. And that's the way dynamic programming has been used quite much in research and engineering development. They develop a solution with dynamic programming, and then you implement a real-time solution and you compare the gap between them. And if the gap is sufficiently small, then you are satisfied with your real-time solution. The cons of dynamic programming is that it's non-causal. You need to have full knowledge of the future trajectory. And the time complexity grows exponentially with the number of states. So for example, if you have one state, you have a quadratic dependence, and then if you go up to 2 dimensions, you get n to the power of 4. And when you go to 3 states, you get n to the power of 6 in terms of the complexity. So you have exponential growth in the amount of arcs that you need to calculate. And 2 to 3 states are often the limit that we manage to cope with in normal situations for vehicles. Beyond that, you have to turn to other methods like numerical optimal control with collocation methods or other types of solvers. To show you a calculation example, we have this following problem with 200 seconds where we have discretized it for 1 second each, so it means that we have 200 time steps. And for the control signal evaluation with dynamic programming, we are making a discretization of the control in 10 points. And then we have a state space discretization with 1000 points. And we say that the evaluation of the mathematical model in a program code for the system takes 1 microsecond to evaluate. If we would do it by brute force, that we make all possible combinations that we can inside the system, then the number of evaluations would be 10 to the power of 200, which will give us 3 times 10 to the power of 186 years. And considering that the universe is only 13.8 times 10 to the power of 9 years, you understand that this is not doable. But if we do it with the dynamic programming and we use the forward approach with discretizing the control and interpolating, then we can solve the same problem in only 2 seconds. So this is quite a good way forward for solving this kind of combinatorial problems. This example was provided by my colleagues at Swiss Federal Institute of Technology. Now we come to the software that you will utilize in the second hand-in task. We look at the provided tools, we look at some case studies that I did for the parallel hybrid in terms of computational time. Hand-in task 2, it's energy management of 2 hybrids, and your task is to optimize the fuel consumption of 2 different hybrids of different structure over some driving cycles using deterministic dynamic programming. You have the parallel hybrid and you have the series hybrid. In the parallel hybrid, we have 1 degree of freedom that we can use to optimize the fuel economy, and that is the state of charge. And the engine speed is given by the cycle because it's controlled by the rotational speed of the shaft, and we have a mechanical coupling, so we cannot do anything there. While in the series hybrid, we can play with the state of charge, and we can also play with the combustion engine. So the engine can rotate freely, and we can go up and down in engine speed between different points to optimize it. So here we have 2 degrees of freedom, state of charge and speed of the engine, whether we should run the engine or not. So it has an opportunity to do more improvements in some ways, but it has also some drawbacks that if we want to be really efficient from fuel to road, we have to take 1 extra energy conversion here in the generator, an extra conversion here in the power electronics, and an extra conversion here in the electric machine. So this costs a little bit extra, but if we have a very transient cycle where we're jumping up and down and have a lot of low load points, then this way of utilizing the combustion engine only where it is most efficient can work quite well. And it's also the transition to a range extender where you build a small engine to provide additional energy so that you can utilize the high density of liquid fuels to get longer range of your vehicle. The task and tools you have is to investigate the optimal control of these two so that you learn about what are the optimal driving profiles for these two applications. So you will sit down, you will solve them and gain experience from how to utilize dynamic programming. And then when you have solved the problems, you analyze the solutions and see if you can generalize the solutions and maybe come up with smart control algorithms that can fulfill these requirements. And your learning goals is to get knowledge about the operation mode of different hybrid topologies, so that you will look at the parallel hybrid and see what modes of operation we have there, and the series hybrid modes of operation we have there, and model them. So you get that experience from modeling hybrid electric vehicles by writing down the equations, implementing the equations in code, and then experience from working and solving optimal control problems, and also see the benefits with different hybrid topologies, where different hybrid topologies are most suited. Coming to the tools that I have provided for you, I wrote the solvers and the skeleton. For both of them, there will be 3 different functions, where you will have one function that sets up the problems that you are supposed to test. You select the driving cycle, you set up the problem. Then you have the solver that does the magic of storing the best path and storing the cost to go values. And that one you don't need to go in, that one is just given so that you don't need to put it together yourself. Your main implementation will be in the arc calculator, where you will have your main task. This program will ask you what are the arc costs for going from one point to the other points. So you will have to do the computation. This one will keep track of the optimal behavior and the optimal cost to go, but you have to provide the values that this one can integrate and use to find the best path. So we will look into how this one is implemented. One thing that we need to do is to pass values. For example, the driving cycle we will load in here, and the driving cycle will influence how much power requirement we have on the vehicle. So you will need to pass the information of the cycle to this function, and in this case we are doing it by using a global variable. So we define a global variable here that is the driving cycle velocity, and then we use the information about the velocity here. So this program will ask your program, you are standing in this time point and you are going to this time point. And for the parallel hybrid, it will also ask you, you have all these possible state of charge levels to go to. How much will it cost to go to all of them? So then you get a matrix problem that you have to calculate all the costs and return the costs for each individual arc. And then when you're finished with that and the program has converged and reached the beginning, this guy ends and pops up to this, and it will return 2 matrices. One matrix which is the optimal cost to go to the end, so you will have the optimal cost, and the other one will tell you what is the best next point to go to. So you start from one point and then you can unwind it. So you go through it and you start, for example, in your initial value, and then you follow the path highlighted by the second argument. That, okay, I know I'm here, and where should I go then? And that you get from the best arc that is stored. So you jump forward until the end. I will go through these 2 problems with some different videos to hopefully help you explain how this works. First, before coming to the video, we will look at the process of constructing a solution. What we have done is we have started here and we have come up to this point. So we are standing now here at 140, and we have calculated everything up to 141. So at 141 we know exactly the best path to get out to the end, and the end here is 50% that we want to get to. So we want to have the state of charge 50% initially, and we want to have 50% at the end. So we see here, these are viable, while these here are not viable, because we cannot jump from here to here. That would require too much current of the battery. But we can go from here and then up through this path and get up to here. But now the question we have here. The middle function knows the cost there, and now it's asking you, so saying, we are here and you have to return to me all the arc costs, all the possible arc costs that could be taken. So return the costs to me. Then it stores this one, so now it knows the optimal cost to go from this point. Then it asks you, now I want to go from this point to all places. So it wants to have the cost calculations for this bundle of arcs. And the optimal was to go here for that one. And the next, now I want the values for these arcs. And when you have returned it, it stores the best way and asks, now I want to know the cost for this bundle of arcs. And when you returned it, it stores the best value. And now I want to have the best path from these and stores it. And now I want all of these. And when it got it, it stores it. And now I want all of these. 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 And here the illustration ends with the arc cost calculation. But I hope that you now have a better vision of the task that you have inside this function. It's this function that should implement these calculations, that gives the basis for being able to construct this data. And here I will show the video of how this is constructed for a given case. So here we start from the end, and then we're constructing. You can see how it's propagating, calculating more and more opportunities, and then just constructing the solution backwards in time until we have at the end reached the initial point. And when we have reached the initial point, then we can start up at 50% initial state of charge and just follow the lines to the end. That was for the parallel hybrid. For the series hybrid, where we have a two-dimensional space and two degrees of freedom, the problem is not as easy to make a video, but I tried to make this illustration. We are doing the same thing as previously. We are propagating from the end, and we are finished up to this point. And at this point, we are then coming and starting with this one. And when we're populating this step with the cost to go, we are in a certain point here. And there we have a matrix of possible arcs to take. And the principle is no different than the previous case. It's just that it's two-dimensional. And you will then need to make a function that can return this two-dimensional matrix to the outer optimizer. Between the parallel hybrid and the series hybrid, we go from one-dimensional arc bundles to two-dimensional arc bundles. And it's just a matter of matrix programming to finish the work there. Now when we have completed the calculations with the method of storing the cost to go and the optimal paths, we can go to the beginning, and then we can start to unwind the solution. So The goal was to start at 50% state of charge, and then we can go forward here. We will see we do some regenerative braking, and we go forward, and we use a little bit electricity in the acceleration, and then we get more regenerative braking. And here, during this part in this solution, we're doing some boosting, and then we're coming up and doing regenerative braking until we end at a point here with 50% state of charge. Here follows a video where you see the unwinding of the solution. When we do the unwinding of the solution, we see how it follows and goes up and goes to the end. And for this case, I can say that it is too sparsely discretized, so we're not getting the really expected solution. So the good thing with deterministic dynamic programming is that it guarantees a global solution, but only within the discretization. And more accurate discretization might be needed to see the details in the solution. So this was what we had previously, and this is something that is closer to what we were expecting, where we will do more regenerative braking and using more boosting in the acceleration and doing more normal driving in the middles, and finally doing a lot of regenerative braking at the end. We will look at another video where we do an unwinding of the solution with a better discretization. Here you can see how it unwinds the solution again, but the characteristics is completely different compared to the first, since we have a better discretization and we get access to more utilization of the battery and state of charge. The problem in the previous was that the discretization was so coarse that we ended up hitting the battery limits, and when the battery limits are hit, the cost is infinite, so we don't get access to the flexibility that the system provides. So, as we said previously, the DDP guarantees a global solution, but we might need to think about the discretization to see the necessary details. Here comes a case study where I have done some simulations using parallel computations and normal computations. And in the normal computation we see here that they scale, and you see here the size of the state of charge window, and you can see how the solution changed. So here we've had 1 per mil state of charge as the steps, and here we have 0.1 per mil state of charge changes in the discretization, and here 0.01 per mil changes. And when we increase the grid, we see here how we increase the time, and it should be that you will see from the next slide. This is a one-dimensional problem, and when we go in discretization a factor 10, the time should increase about a factor 100. Here it doesn't really go so, because here we are hitting some other limits in the CPU. It's not the computations, but it's allocation of memory when we do all the function calls that comes in and plays a bigger role. But when we come up and get bigger and bigger computational structures, we see that here it's pretty close to at 100, at least size-wise. Here you see that this cycle with this accuracy takes 800 seconds to solve, which is just about 13 minutes. And if we use parallel computing, so we use parallel for loops inside the solver, we can actually get a little bit better in terms of the top. So with parallel computations here, I'm using my server that has 12 cores, so I'm getting 71 seconds to solve this problem with parallel computations. But when we come down to really small discretizations, the overhead of allocating memory and shuffling things back and forth in the parallel settings costs more than just doing the computations. But when we come up here, we can do an even finer grid within less time than what we had here. And in this case, we went up a factor 2 in the number of grid points, and that would mean about a factor 4 in computation time, which seems reasonable here. At least it's in the same ballpark. Your implementation task, when we look at the complexity of the algorithm, we have for the parallel hybrid 2 dimensions with number of x and number of y in the 2 dimensions points. We have in the 2 dimensions we have number nx in one dimension and ny in the other point. And we have nt is the time points that we have in the grid. At each step, nt, we have to evaluate the points in this sheet. And for all points, we have to evaluate all possible future states, all possible potential candidates. So that is why we get this time complexity. So it's quadratic in each dimension and linear in time. K here will be connected to how complex the model is, how much time it takes to evaluate the function once. So in this case, if we would have the same, if we would have 2 dimensions that we have here, p is 2, and we get this n square to the power of p. So this is exponential complexity, and it's called exponential curves of dimensionality of the problem. So for your problem and for your work, I suggest that you work with pure arc costs and debug your functions, and you use MATLAB matrix mathematics so that you get efficient computations, so you don't do double for loops for the series hybrid. And you start with smaller problems, so when you have looked at the arcs and seen that you have gotten the right arc costs, you, for example, start solving it for this hump so that you see that you get reasonable solutions for that one. And then you jump up to bigger and bigger problems. And when you're convinced that you have the solution ready, you increase the problem size and level of detail. Normally, a reasonable grid size for the series hybrid will take about an hour to complete for the European cycle. It will be longer for the American and the WLTP. Anyway, I think this is like the crown jewel of the course, where you can generate the optimal control strategies for very complex models. You have to know of the drawbacks and advantages of it. And you have a parallel hybrid example here, where you can see the operation presented in slightly different way. Here, when we're starting at 60% and we're supposed to end up in 60%. But as you can see here, this is a region where we cannot jump from this point and get all the way up here. So here you see how we use the electricity to go up and take this first bump. Then in this part here we go down a little bit, and then we use pure thermal energy. So we use pure engine. We don't do any boosting. We drive here and then we go up here, and here is pure regenerative braking. We can see that because the state of charge increases. And here again we take electricity in the beginning, and then we run some thermal engine to reach the higher speeds, and then we go up and down depending on where we are. This is regenerative braking, and finally we have a regenerative braking in the end. The tool that you will be working with can provide this kind of information for you about what is the optimal path to get from the beginning to the end. For the parallel hybrid, we can also do it for the complete cycle. In this case, the unwinding is not there, but you start at the 0.6, and then you can see the orange parts here is where we'll use combustion engine, and in all the regenerative braking we're only using the electric machine to do the regenerative parts. And we can see how we go through and how we should act in the different points. So here up at the maximum points we do a little bit of load shifting, but at the maximum power point here we need to do some boosting to be able to perform acceleration at this high speeds to reach 120 kilometers an hour. One of the things I also want to highlight to you is that the system with the cost to go is also a feedback solution. So for example, if we get the disturbance, let me jump back to this point. So this is where we should start, but there comes some disturbance in the traffic, And we cannot do all the regenerative braking here, so we end up maybe at this point. But when we have gotten this disturbance here, and we're still going to the same destination, we can now apply the control actions that will take us back up unto this point optimally from any of the points here that have been stored. So here is an example of the feedback solution that we get from the solution to this dynamic programming problem. One thing that we need to do then, if we want to have access to this feedback, is that we need to store the solution of this problem. So we need to store the cost to go, and we need to store the optimal arcs. Actually, we only need to store the optimal arcs from the points where we are to get to the endpoint optimally. That's the crown jewel of this course, where we can look at different ways of solving the hybrid electric vehicle control case. With that, I thank you for your attention and give you the reflection that this is offline control. You have to have the full cycle information available, your full trip available, but then you can do the planning optimally. Next lecture will be on real-time control, where we will look at methods of developing real-time controllers that are based on optimal control theory. It will be equivalent consumption minimization strategy that is a result from minimizing the Hamiltonian and Pontryagin's minimum principle. And with that, I thank you once again for listening and hope that you will return for the next lecture. Bye bye.